Welcome, little scientists, to our experiment today, breaking the boundaries. My name is Bo.
And I'm Ryan.
We are from the Cremer lab at Penn State.
We study the chemistries at the cell surface. What we're interested in looking at is little things that interact with any type of biological system and the surfaces that go along with it.
Another thing that we are curious about is how water surrounds living systems. As you may know, 75% of our body is water. So basically, every component in our body, every cell or cellular components are interacting with water. And interesting chemistry happens at the boundary between water and the cell membrane.
Whenever two things come together, the place they meet is called an interface. In general, these two objects can be anything from a hard surface like metal to even the air that we're breathing right now.
Another example of the interface is something that you may have heard of. That's the interface between the air and water. And this interface has a very special property that's called the surface tension.
The surface tension is a very complicated thing to understand, but put simply, water acts like a teeny tiny invisible sheet and allows water to do things like this. It also allows us to float a piece of metal on top of this glass of water.
So here we have a paper clip, and surface tension is what allows this paper clip to float on top of water.
But if we apply any pressure to this, it'll break the surface tension and fall to the bottom.
But air isn't the only substance that will create an interface with water that has a surface tension. Oil will do this as well. So you may know by now that oil doesn't mix with water. Here I have on the left a glass of oil and on the right a glass of water. Let's see what happens when we pour the oil into the water.
Whenever you give it a couple seconds, you'll see that the oil floats on top of the water. And right here, you can see that this is the oil-water interface.
All right, are you guys ready for a little experiment?
Here's all the materials that you'll need for today's experiment. We'd like to emphasize that you'll need glass cups and not plastic cups, as plastic will interfere with the experiment. All other materials, please refer to the list given.
All right, so here we have 3 glasses, one filled with water, one filled with oil, and then the third one half filled with water, half filled with oil. Now we're going to show you how to prepare the third glass.
So what we're going to do is we're going to take our water, fill it up just a little bit, and then we're going to take our oil. And this part's very important to prevent bubbles. What I'm going to do is I'm going to tilt the glass slightly and just pour very slowly and carefully so that we don't get any bubbles. And that's how we make this.
So now, let's pick your favorite color of food coloring dye and add 1 drop to each glass and see what happens.
So, my favorite color is red. So, what we're going to do is we're going to take our food droplet dye and we're going to put it real close to the interface here for the water. So if we drop 1 drop real slow, you can see that it drops to the bottom of the water. Now, if we do this for the oil, it also drops to the bottom of the oil. But if we go over here to our oil-water mixture, and we drop it real close to the interface, we're going to see that whenever we drop it down, the food droplet dye stays here at the oil-water interface.
Okay, now let's see what happens when we add soap to the half water, half oil cup.
So what I'm going to do is I'm going to take this jug of soap right here, and I'm going to slowly add 1 drop of soap to it. We're going to wait for the soap to reach the interface. And maybe need a little bit more soap. Whenever we added soap to the mixture here, the soap acted as a knife and cut up the oil-water boundary, which allowed for the food droplet dye to drop to the bottom of the glass.
Cool. Now as a scientist, we like to explore how system changes when we change variables. This is the basis behind scientific methods. So let's see if we can modify the strength of the interface.
And so now, instead of just using water, we can use a more viscous liquid such as corn syrup. And so the corn syrup is a very sugary mixture that's going to have a higher surface tension than just pure water. So what we're going to do is we're going to have 3 different amounts of corn syrup water mixtures, a 25%, a 50%, and 100%. And so with these 3 glasses, I'm now going to show you how to make each of these mixtures. So in the 25% container, what we're going to do is we're going to add 6 tablespoons of water. So 1. You may make a mess just like I did. 4, 5, 6. So that's the amount of water that we'll need for the 25% mixture. For the 50% mixture, we're going to need 4 tablespoons of water. 1, 2, 3, and 4. And so this last glass here is 100% corn syrup, so we will not need any water. So now, if I move the water out of the way, we're going to add the necessary amount of corn syrup that's needed. So in this 25% glass, we're going to add 2 tablespoons of corn syrup. And as you can see, whenever I pour this in, it's very viscous, so it's going to pour very, very slowly. So there's 1. Try to get as much of the corn syrup out as possible. May have to tap it a little bit. You can see it's even stringing off the side here. And then 2nd. Okay, so that's for the 25% mixture. For the 50% mixture, we need 4 tablespoons. One. 2. You can see this takes a while just because of how strong the interactions with the corn syrup is. 3. 4. Okay, and this 100% corn syrup is going to need 8 tablespoons. So this may take me a little bit of time. Or we could be smarter and just pour out from the top. And that should be pretty good right there. It's a little less than the other cups, but it should work. So, now, what we're going to do is we're going to add the... Oh yeah, we have to stir first. My bad, guys. So, we're going to stir these up. You can see it's going to take a little bit. You may even want to use the bottom here, because it just allows you to get a little bit more in there. That's the 25%, the 50%. And this should be stirred pretty well. And then the 100% we don't have to stir because it's 100% corn syrup. So now, if we add some oil to it to make our corn syrup oil interface, remember to add slowly. %. Try to prevent bubbles as much as possible. And then the 100%. And so, that's how we make our 3 solutions. So now we're almost ready to add our food dye droplets to each of these solutions. But first, let's think back to what the oil-water interface looked like whenever we added a food dye droplet. Let's think of the interface as just a trampoline. You can see that whenever we add the food dye droplet, it deformed the interface quite a bit. Now, let's see what happens whenever we add the food dye droplet to each of these mixtures. Remember to add the droplet rather close to the oil without touching it. There's for the 25%. The 50%. And the 100%. And so now, let's look at what the trampoline, the interface, looks like, and then make predictions from there on what we believe the amount of soap that we'll need to add for the food dye droplet to drop to the bottom of the glass.
Many secret patties later.
Now that we've made our predictions, what we're going to do now is see how many droplets of soap it takes to drop the food dye droplet to the bottom of the thing. Let's start with the 25% mixture. 1. Ooh, 2. That was a little big drop. Might have something here. If you leave it go, it'll drop a little bit. But let's try for a 3rd drop. 3. 4. 5. And there it goes. 5 droplets for the 25% mixture. Let's try the 50%. 1. 2. 3. I'm going to count that as 4. 5. 6. Oh, we got a little bit of movement. Maybe just a little bit more help. Oh, nope, 6 for the 50% mixture. Let's try the 100%. 1, 2, 3, 4, big bubble there. 6, 7, 8. Is our prediction looking good so far? 9, 10, 11, 12, 13, 14. Wipe it off a little bit. 15. You can see that it's not really dropping very well. So what we're going to do, even after a huge squirt, 100% is not going to drop. This is because the 100% corn syrup is really, really viscous and has a really high surface tension.
Alright, little scientist, what happened? And why do you see what you see? I made a little table here to record the number of drops of soap that you need to add into each corn syrup solution. And from top to bottom, you go from 0% corn syrup to 100%. And the number of drops of soap required also increases. And that means when you have more corn syrup in the solution, the boundary between the oil and the water phase is harder to break. On the right over there, I had a little drawing to draw your attention to the shape of the boundary between the oil and the water phase. The blue line represents the boundary. The oil phase is on top, and the water phase is below the blue line. The red circles represent your food coloring drops. So, when you go from 0% to 100% corn syrup, you can see that the blue line, or the boundary between the oil and the water phase, deforms more when you don't have corn syrup in the solution, and it's basically a flat line when you have 100% corn syrup. That's the indication of the stronger the boundary between the oil and the water phase when you have more corn syrup in the solution. And that also explains why you need more soap to break the boundary. Because remember, we mentioned in the video earlier, soap acts like a knife to break the boundary. So to bring you back to the trampoline example that we showed you before, when you are jumping onto the trampoline sticks. But when you have a steep trampoline, then it may not deform as much. And that's similar to what you see in the 100% case. So, how's your experiment going, little scientist? Everything is going well? You notice something odd? Well, as a scientist, we are not always lucky. We are constantly troubleshooting and finding out ways to improve our experiment. So Ryan is gonna tell you a few little tricks to make your experiment a success.
The very first one that is probably most probable to go wrong is that the oil-water interface is not extremely strong. So what you may see is that whenever you drop the food droplet dye in, it just falls right through, or within a couple seconds falls right through. One way to get another piece of data would be to try a 10% corn syrup mixture. This will help increase the surface tension just slightly, enough to keep the food dye droplet at the interface. The way that you should make the 10% corn syrup mixture is to use 1.5 tablespoons of corn syrup for 1 cup of water. That should solve your issue. If not, try higher concentrations of corn syrup until you're able to get 1 food dye droplet to stick.
So, do you remember at the beginning of the video, we said that the material of the cup that you're using is important? I just want to re-emphasize that. So instead of plastic cup, you should use a glass cup to make your experiment successful. And your glass cup should also be free of any soap or oil. It has to be clean for the experiment to work.
Let me show you what a food dye droplet looks like whenever you use a plastic container. You notice the difference? Yeah? The food dye droplet sticks to the side of the container. This makes the experiment a lot more challenging than just using a glass container, because there's now a three-way boundary. The oil, water, and plastic, where the plastic and the food dye droplet interact very strongly.
And the second thing that we noticed that we have problem with in this experiment is how to deal with the viscous corn syrup. So we suggest that you take time and be patient when making the corn syrup. So just pour the corn syrup in the water and stir it slowly using a spoon until it completely dissolves.
The final issue that we could think of was, how did you drop the food dye droplet? If you dropped it from too high, the food dye droplet's going to fall through the oil very quickly and probably break the interface just by how fast it's dropping with the weight of the food dye droplet. Make sure you're dropping it from just barely above the oil surface, and so that it goes slowly down to the oil-water interface. Those are all the issues that we were able to think of. We have contact information that you can reach out to us if you experience any other type of issue. JK, there's actually one more issue that we could think of. There's actually one more issue. So, depending on how much oil you put at the oil-water interface, if you use a small amount of oil, it slows down the food dye droplet just enough. But if you add more and more oil, once the food dye droplet hits the oil, it slows down, but the more oil there is, it gets more and more time to speed up. That could also cause an issue at the oil-water interface eventually.
So, we've come closer to the end. In summary, during this experiment, you have seen the food coloring droplet fall to the bottom when you have water-only or oil-only containers. But when you mix oil and water or oil and corn syrup together, the food dye droplet doesn't fall. Instead, it stays at the boundary between the oil and the water. And the surface tension is what allows this behavior to happen.
So in this experiment, we were able to modulate how strong the surface tension is by using different concentrations of corn syrup, anywhere from 0 to 25 to 50 to 100% corn syrup. We were able to test how strong these interfaces were by adding soap. Soap is pretty special because it's able to interact with both the water, or corn syrup, and the oil. So what it ends up doing, if we go back to our trampoline example, it acts as that knife, and it cuts up the interface and allows the food dye droplet to fall to the bottom. Even before we added the soap, we were able to get a good idea of how strong the interface would be. We were able to look at how the trampoline looked. We saw that the 0% corn syrup was very deformed, whereas the 100% was a flat surface. And that's how we were able to get a good clue on how strong the interface actually was.
So the interactions at the interface is very important. Our body actually uses surface tension to keep important molecules where they're supposed to be. Another example of the use of surface tension is in water striders. Those are little bugs that can float on top of water thanks to surface tension. Another consequence of surface tension you can think of is the formation of little rain droplets on your window.
We'd like to thank all of you for listening and trying our experiment. If you have any questions or concerns, feel free to reach out to us at our contact information given in the experiment handouts. We hope you enjoyed our experiment. Bye, friends.